Hey everybody, we're back. Mr. Hayes' World of Math. We're reviewing AP Stats. I know I sound like a broken record, but we're almost halfway there. Actually, we are halfway there after this lesson here. We're on day 6. We are doing random variables. And so it's very similar to what we do with probability, but we're just gonna take it another step here or there. And so we are going to jump right in and we're going to move over once I remember the correct keystrokes to jump into this. All of this is located in a link down below for the free 3-week AP Prep course. All of it is just stuff that's available on the AP website, reformatted in such a way that you can easily use it. There's links to stuff at Khan Academy, all sorts of things. If you have any questions, go ahead and look me up. And while you're down there, hit subscribe, hit like, leave me a comment or 10, and we will go from there. So the first situation is this. We've got approximately 3.5% of all children born in a certain region are from multiple births, meaning twins, triplets, etc. Everybody else, and of those children who come from multiple births, 22% are left-handed. Of the children born in the region of single births, only 11% of those are left-handed. So the first question is, what's the probability that a randomly selected child born in the region is left-handed? So this is very similar to the setup of what we did yesterday when we were talking about probability. Just a tree diagram. I've got over here multiple birth or single birth. Multiple births are 0.035, 96.5% for the remainder part. Kick it over here. Are they left-handed? Great, that's a 22% chance. 78% chance not, 11% chance if they're left-handed, and a single birth. So then what we need, since we're looking for a probability of left-handed, is we're just going to follow the tree to the left-handers. So we're going to do this. And as you go, you're going to multiply the different probabilities as you go, add them up at the end, boom, Bob's your uncle, and you have your number. So in this case here, we will end up having this. The top line turns out to be just under 1%, 0.0077. The other one is just over 10, so 0.1062. Add them all up, and we have an 11.3% chance of getting somebody randomly who is of a left-handed person. So if we go down here to part B, what's the probability that a randomly selected child born in the region is a child from a multiple birth, given that the child is left-handed? So you know that the kid who's chosen was left-handed. What's the probability that they were from a multiple birth? So the setup for that one, remember, is this. Now the given focuses in on what we're talking about. So what's the probability that they're a multiple birth if they're given left-handed? So when we do that, if we look back up here, we're only caring about the people who are in these yellow lines. These other people we're not going to worry about. Why? Because we know we picked a left-hander. Those people are right-handed. We're not going to mess with it. So that means that our population is the person we pick from has a population chance of 11.39%. So instead of being 100%, that is going to be our bottom denominator there. So probability of getting a left-hander, probability of both left-hander and a multiple in the top. So you get this. We have our 11.39% as our population, since that's the group that the person is from, and we know that. And then the chances that they were from multiple birth and left-handed is the 0.0077 number. Divide that out, and whoop, there it is. So if you know that you have a left-hander, there is a just under 7% chance that that person also came from a multiple birth. Twins, triplets, quadruplets, etc. And then for part C, a random sample of 20 children are born in the region will be selected. What is the probability that the sample will have at least 3 children who are left-handed? Couple of things. So now we're starting to get into those binomial distributions. So now what you want to think about is that we want to have, what's the probability that we have 3, 4, 5, 6, 7 all the way up to 20? Or another way of saying is, what's the probability that you don't have 0, 1, or 2? And then we take the difference from that, okay? So a couple things to think about. You have your binomial CDF. Now binomial CDF only covers, so I've got, actually let me do it for typing. So we've got like, we could have 0, we could have 1, we could have 2, we could have 3, we could have 4, we could have 5, we could have 6, etc. 19, and 20. Okay. So we want everybody in, we'll do highlighting. We want everybody here. 3 or more. So what's the probability the sample has at least that? Now, when you do binomial CDF, it only goes up from the left. Okay, so this number right here that we're typing into a calculator is only this part. Okay, so that means that whatever that number turns out to be, which in this case here is about 60%, then we need to go through and we're going to subtract that out. Okay, so that means that the probability is right around 60%. So we are going to go through and we're going to do 1 minus point, let's go 5 decimal places, 976. So it's going to be right over 40%. Actually, it's going to be 40.24 or 40.24. And that's going to be the probability. So just be really careful in terms of the setup of that, because again, binomial CDF will only go up until we see what's going on, and then everything else will go from there. Now, when you type this in into your calculator, the first thing here is going to be trials, and then you're going to have your probability. And then the last one is going to be your X value that you're looking for. All right, so those would be how you would label this out. And that's it. So you can see it relies a fair amount on the probability. They just take it a little bit extra from there. Now, the next problem that we have over here is going to go through and give us, you've got a rocket launcher set up. The old version of the igniters fail 15% of the time. They make a new one, and they want to make sure that it should be more successful. So the company engineer develops a new igniter. To test the performance of the super igniters, the engineer uses the following process. One super igniter is selected at random and used in a rocket. The rocket launches. They put another igniter into the is selected and randomly used in a rocket, and you just keep on going. You're going to do this until you have a failure, or until you hit 32 super igniters light successfully and launch rockets, whichever one comes first. Assume that super igniter failures are independent, so one's not going to affect the next. So for part A, if the failure rate of the super igniters is 15%, what's the probability that the first 30 super igniters are going to fail? Or, won't fail, excuse me. So that is just simply going to be, what's the probability of success? And then you're going to have 20 of those. So we've got the probability of success is 1 minus the failure. So we get 85% to the 30, or 0.85 to the 30th power. So you're going to turn out that having 30 of them happen without any issue is going to be 0.0076. So very unlikely, but we'll get more to that in a second. For part B, given the fact that the first 30 super igniters have successfully launched, what's the probability that the 31st fails or the 32nd fails? So if you come down here, the 31st failing is just going to be 15%. The first 30 we don't care about. Why? Because they're independent. Those 30 up until that point have no bearing on what's going to happen on the 31st rocket. So you've got that. Now, so if we get a failure on the 31st one, there's a 15% chance of that. The 32nd one would mean that we didn't fail the first time, but failing the second time. And so because of there, you're going to have success times failure, which is going to be 0.85 times 0.15, which is 12.75%. We're going to add those together because, much like the tree diagram, it's the same idea. So there is a 27.75% chance that if the first 30 rockets were successfully launched, that you're going to have a failure either on the 31st or the 32nd rocket failure, which ironically is the same thing as the first and the second, as long as, whenever you're there. Given the first 30 super igniters successfully launched rockets, is it reasonable to believe that the failure rate of the super igniters is less than 15%? And explain. So again, this is, if you can mention alpha levels if you want, as the probability of 30 successful launches is 0.0076 purely by chance, then if the true, I should have added, actually, I could just cross that off, is extremely low, less than 1%, or you could even say less than 5%. It is highly unlikely that the failure rate of the is highly likely, excuse me, that this failure rate of the igniter is less than the 15% that's assumed. Okay, I think I said that correctly. So anyway, so that gives you a basic for what's going to happen. So again, a lot of the probability stuff, and then they're just going to ask you to kind of push it a little bit further. That's it for this one. We're going to move into some simulation stuff and then hit confidence intervals before we have our next break and our quick little assessment on day 9. And then we are in the home stretch. So we're now officially done. We're halfway through the review. Hope everything's going well for you. If you have any questions, throw them down in the comments. We'll talk to you soon.